Welcome to this online course on linear algebra. Before we dive into the topic of vector space, let's take a moment to understand what linear algebra is and why it is such an essential area of mathematics. So linear algebra is the branch of mathematics concerning linear operations, linear functions, and their representations, right, through the matrices and the vector spaces. So it is the foundation of many areas of mathematics and is widely used across various disciplines, including science, engineering, computer science, economics, statistics, etc. So linear algebra is incredibly versatile and has numerous practical applications like computer graphics. So linear algebra is used to manipulate images and create animations. Like we do transformation, rotation, and scaling of images, which are achieved using matrices. And here is the significant importance of linear algebra. Uh, it has numerous applications in engineering because it helps in solving system of linear equations that model real world problem in electric circuits, statics, right, and the dynamics. Also, the linear algebra is playing a vital role in data science, like techniques such as principal component analysis, we say PCA analysis, right, for the dimensionality reduction, and various machine learning algorithms rely, the heavily on linear algebra. Also, it has numerous applications in economics, like linear algebra is used in input-output models and optimizing resource allocations. Uh, Also, you have seen that the physics also has its numerous applications. Like it helps in understanding quantum mechanics, electrodynamism, and general relativity. Yeah, so with this understanding of the importance and applications of linear algebra, we can appreciate the significance of learning the various units in linear algebra. Here we start with vector space. So actually this form a core concept in this field. Okay, so we begin with the vector space, the definition of it, and some of the examples in today's class, and we will be talking about the linear transformations, determinants, matrices, the matrix representations, and so many other things like Jacobian matrix, eigenvalue, eigenvectors, much more in this course. So let's begin with the vector space with this definition. Definition of the vector space. Right. So a vector space denoted as V over a field F is a set equipped with two operation. Right, the two operation means the vector addition and the scalar multiplication. So here we say the vector addition means an operation plus from V cross V to V that assign to each pair of vectors alpha beta from the vector space V, a vector that we get by adding the two vectors alpha and beta also in V. This is called the close under vector addition, and also the close under scalar multiplication. So this is an operation again, but this time this operation is dot from F cross V to V, right? And that assigns to each uh, scalar. Here I should let me just draw it. The scalar to a scalar, right? This scalar, let's say, is f from the field f, and each vector let's say this vector is alpha from V. A vector that is multiplied with the scalar a, right, also is in V. Then it is called the closed under multiplication. So this must have to be satisfied if the V is vector space. Okay, so these operations, must satisfy the following axioms for all vectors alpha, beta, and gamma from V, and all scalars a, V from F. Okay, so the axioms are vector addition, and under vector addition we have some properties of it. Is the commutativity, of course, the commutativity of addition. Okay, so this means alpha plus beta equals to beta plus alpha. So this essentially means, like, if you add two vectors alpha and beta, then it is the same with adding beta with alpha. So this is commutativity. Second property is associativity. Right? So this means if you are adding alpha plus beta and then adding gamma, is same as doing first adding beta gamma and then adding alpha. Next property is identity element of vector addition. Sometimes we call it law of zero. Okay, whatever we say is the same thing. Okay, all right, so the law of zero is like there exists a unique element 0 from V such that zero plus alpha equals to, you can write alpha plus 0 because it's commutativity, so it is obviously alpha for all alpha in V. Okay, so for every alpha you should get 0, so that you add with that 0 you get the alpha itself. So D inverse element of addition. So for every alpha in V, there exists a unique element minus alpha belongs to V such that alpha plus minus alpha equals to 0. So these are all the axioms on vector addition. Second, scalar multiplication. Number A is associativity. We don't have commutativity in scalar multiplication. We have the associativity. Okay. Associativity of scalar multiplication, of course. Which means if you are multiplying b with alpha and multiplying a is same as multiplying a and b and then alpha. Next one is identity element. Okay, of course, of the scalar multiplication, also called as law of zero, means 1 times alpha equals to alpha for all alpha in v, right, where this 1 is the multiplicative identity in f. Number 3 is for the distributivity. So first one is distributivity of the scalar multiplication. Distributivity of scalar multiplication with respect to vector addition. Okay, so we have two distributivity. The first is distributivity of scalar multiplication with respect to vector addition, and we have the distributivity of the scalar multiplication with respect to the field addition. Okay, so here this means a times alpha plus beta is distributive, can be distributed as a alpha plus b beta, right? Next is distributivity of scalar multiplication with respect to field addition. This means if you are adding two multiple scalars and multiplying with alpha, this can be distributed as a alpha plus b alpha. Okay, so these are all the properties, the axioms of the vector spaces. So if a vector space V over a field F means a set of if is a set, the equipped with two operations, basically vector addition and scalar multiplication, and in vector addition it should satisfy these four different properties, and in scalar multiplication it has to satisfy these two properties, and in the distributivity this has to satisfy with these two properties. So a set V will be the vector space if it satisfies these 8 different axioms. Alright, let's see what happens with some of the examples. We will start with some example here. Examples. Okay, so the first example we will see it with the n tuples. N tuple space. Okay, we say this vector space. So n tuple space. Let's say this Fn. Okay, so we will see this is a vector space. Okay, so in fact we can see the axioms of the vector space that we have just listed out in the definition and see if it satisfies all the 8 different axioms that we have listed out. So in fact Fn is the set of all order n tuples of elements of f such that uh, okay, let me clarify it. So Fn is the set of all ordered and tuples of elements of f, means you can also write this as Fn is the set of all order n tuples, right? This is one order n tuples, right, up to xn, the order n tuples, right, with each xi from f for all I equals to the n index. Okay, so since if u equals to u1, u2, and so on, un, and v is v1, v2, and vn are two different vectors in Fn, right? Yeah, because u and v both are n tuples, so they are from the set of Fn, right? Then you see u plus v equals to u1 plus v1 plus and so on un plus vn. Okay, we use this u and v alphabet frequently, so try to identify my u and v. Sometimes I get confused myself, so yeah, this is the way I write u and v, so get it familiar with. Okay, so this is again in Fn, right? Because you see these are again the vectors, and that we get from adding this the n tuples, right? So yeah, this satisfies the condition vector under addition. That means it is closed under addition, so if you want it, just you can write like, because this is in Fn, because each ui plus vi is in f, right? Okay, so again you can see the scalar multiplication av will be av1 plus I'm sorry, this is av2 and so on avn, right? So this is other n tuples also will be in Fn. So it shows this satisfy the vector addition and scalar multiplication. I mean, these are closed under vector addition and scalar multiplication. Yeah, and this is because you can write it because each avi is in f, right? So let's see what happens with other axioms. So for all vectors u, v, w in Fn, and for all scalars a, b in f, vector addition, we will check all these 8 axioms that were listed out. So the vector addition, first we will see either this is commutative or not. Okay, so we will see if it satisfy the u plus v equals to v plus u or not. So let's see. U plus v means we have already seen that this is u1 plus v1 and then so on un plus vn, right? But it can be written as v1 plus u1 and so on vn plus un, right? Because this all u1 v1 these are all the elements of n tuples. We can just write it, and you see this is just nothing, this is just like v plus u. So you say this is satisfying the commutativity. The next one is associativity, right? So this means u plus v plus w. Let's first see what happens with u plus v. Okay, so the u plus v means again u1 plus v1 and so on, un plus vn, and plus w is w1, w2 and so on, wn. Okay, so this is now u1 plus v1 plus w1, right, and so on, u1 plus v un plus vn plus wn. This can also be written as u1, u2 and so on, un plus v1 plus w1 and so on, vn plus wn, right? So this is nothing, just u plus v plus w. So we see this also satisfies the associativity of addition. Next, we will see identity element of vector addition. Okay, so for each zero vector, that is 0 equals to, we could write like zero vector like this way. Yeah, you feel free to write that. So this is 0 0 and so on, 0, which is in fn, right? Yeah, this is an n tuple, n numbers of zeros. This x is the additive identity because you see b plus 0 equals to v1 and so on, vn plus 0 0 0, which is equals to nothing, just v1 plus 0 and so on, vn plus 0. This is essentially the same as v1, v2 and so on, vn. Okay, so this is just v. So what we found here is v plus 0 equals to v, and we got that 0 is an additive identity. Inverse element of addition, right? So this satisfy with, like, for each v equals to v1, we know up to vn, this is in fn, there exists minus v, which is equals to minus v1 minus v2, of course, up to minus vn, in again fn, such that v plus minus v equals to v1 plus minus v1 and so on, vn plus minus vn. This equals to just 0 0 and 0, right? So which means the zero vector. So we also found the inverse element of addition. Okay, so let's go with the second exams, that are scalar multiplication. In the scalar multiplication, we will see the associativity first, right? So for the associativity, we will check what happens with a, b, v. So here a, b, v means b, v1, right? b, v1, a, b, v2, so on, a, b, Okay. A B V N. Okay. So this is the same thing as saying A V V1 and so on, A B V N, and this means nothing, just A B V. So this also satisfied part A, and part B is the identity element of scalar multiplication. Here we see um, the identity element of multiplication is 1, so 1 times V equals to 1 V1 and so on, Vn equals to 1 V1 and so on, 1 Vn, which is again the V1 and so on, Vn, right? So this is nothing, just V. So this condition satisfied. Let's see the distributivity. So first of all, we will see the distributivity of scalar multiplication with respect to vector addition. This is A with the vector addition of V and U. This is A times U1 plus V1 and so on. A is already written outside, so okay, UN plus Vn. Okay, so this means A UN plus V1 and so on, A UN plus Vn, which means AU1 plus AV1 we are doing the distributivity with vector addition, right? So AU1 plus AV1 and so on, AV1 AU1 here should be plus, right? AUN plus VN. Okay, so this is same as AU1 and so on, AUN plus AV1 AVN. Okay, so now this is A times U and this is B times, oh sorry, this is A times V. So what we got here is AU plus V equals to AU plus AV. So this is the distributivity of scalar multiplication with respect to vector addition. Number A. So now the distributivity of scalar multiplication with respect to field addition. So here A plus B times V equals to A plus B and B1 and so on, Vn. This is same as A plus B times B1 and so on, A plus B times Vn, which is equals to AV1 plus BV1 and so on, AVN plus BVN. Okay, so this is equals to AV1 so on, AVN plus BV1 and so on, BVN, which is nothing, just AV plus BV. So all the property that we see, addition, vector addition, scalar multiplication and distributivity are satisfied. So likewise you can check other examples such as the set of all polynomials with coefficients in a field F forms a vector space over F. Okay, so yeah, you can check this is also a vector space. So for this you can go with all the 8 axioms of vector space and see if all of them are satisfied with the polynomials. Okay, the set of all polynomials. So the set of all polynomials, yeah, the polynomials is like px equals to I runs from 0 to n ai xi, right? So these are the forms. So here you can just consider one polynomial function as the p, other you can consider as q and r, and then you will see like the vector addition and scalar multiplications properties. Either it satisfies okay, for example, for the qx I xi. Okay, so and then see if it satisfies all these axioms of the vector space. So here you can see the other very interesting examples. And here you see the other interesting examples, which is so you can check other examples like the space of polynomial functions of degree at most 2 over a field F is a vector space. Okay, you can check that out. It's very interesting. You will see this satisfy all these axioms of vector space again. Number 4. Here we will see if it is a vector space, but actually the space of polynomial functions of degree exactly 2, okay, 2 over a field is not a vector space. So how can we check it? Let's see it. In fact, let's consider the space of polynomial of degree 2 over a field F, right? So we denote it, let's consider the space P, we denote it as P star 2 over field F. Okay, so this we just denote, and the This is of the form Px equals to a naught plus a1 x plus a2 x square. This is where, because this is a degree 2, a2 must not equals to 0, and we are considering the 2-degree polynomial. So we will see either this is closed under addition and closed under the scalar multiplication or not. So closure under vector addition. Okay, so let Px is a naught plus a1x plus a2x2. Of course, a2 is not 0, and qx equals to b naught plus b1x plus b2x square. B, the polynomials in P star to F with A2 not 0 and B2 not 0. Okay, so then what happens with Px plus Qx? So this is equals to A naught plus B naught plus A1 plus B1 x plus A2 plus B2 x squared. Okay, so for Px plus Qx to be in P2 star to F, we need A2 plus B2 not 0. Yes, however, A2 plus B2 could be 0, meaning the result could be a polynomial of degree less than 2, thus P to F is not closed under addition. Right, because even the A2 and B2 are not 0, but A2 plus B2 can be 0, because for example A2 equals to maybe 2 and B2 equals to minus 2, right? Because this is not 0, this is not 0, but A2 plus B2 equals to 0. So this can be the condition, and this will not be closure under addition. So this will be sufficient to show that this is not the vector space, because this violate one of the condition of vector space. So among these 8 conditions, if one of the condition is just violated, then we say this is not the vector space.